Hello, so today we are going to do this problem called delete nodes with given values and return a forest, which basically essentially what the problem is that we get a binary tree like this one here. So we have a binary tree and we have a list of elements that we want to delete from that binary tree. And after deleting these elements, we will get multiple trees, and multiple trees constitute a forest, and what we want is to return the list of these trees. So for example, in this binary tree here we have these elements and we want to delete nodes of value 9 and 5, and we are guaranteed that the tree has distinct values. So in this example here, what will happen is that we will end up with, we will need to remove 9 and 5. So we will end up with the tree. So removing 9 means we'll end up with 1 and 12, right, as two trees, and then we'll end up with, on this side, 6, 4, and then 3, and then since we delete 5, 5 will be removed. Removing 5 is easy here because it's a leaf node. So we'll end up with these 3 trees, and this is what we want to return. We want to return the roots for each of these 3 trees, and that constitutes the forest. So we want to return a list of these in a way. So what this would mean is that we can return this one and this one, and this list here is the forest that we want to return as a result. And so if we look at this problem a little bit here and just specify what we are looking for here. So the unknown in this problem is the forest result after removing nodes with values in to delete array, right? So this is the first. And what do we have as input? We have the root node, right, of the tree, and we have the to delete list. So this is our unknown and our data. So let's figure out here what we did. Let's just think about what we did here. So what we did is we had a node, and that had a left subtree and had a right subtree. Okay, and we have two possibilities. Either the node is in the to delete list or set. We can convert it to a set just to make checking if a value is in it easy or not. If a node is in it, we have two choices. So basically, node in to delete, right? At that point, what we should do is remove this and remove this, and we will end up with left and right as a part of the forest. But we will need to also process these two because maybe they contain other elements that are to be deleted, and that we need to also cut the left subtree into multiple trees that are in the forest, right? So we need to also recurse on left and right. And then once we recurse on left and right, we will get a result and we will add that to the forest, right? Or the node is not in the to delete. At that point, we can just add the node itself. And then later, if we find that another element here in the left tree is to be deleted, we can just cut its ties with that node. And that node, since it's already deleted and we will be manipulating its reference, we would remove it like we did here for 6, 4, 3. So we will recurse on 6 is not into delete, so we'll recurse on 9, 1, 2. And we want to delete 9, so we can just return to the parent null. So that 6 says 6.right is equal to none, and that way we will delete it, okay? But before doing all of this, let's just break down what we are asked here, right? So let's just think about some parts of the problem here. So first, we know that when a subtree becomes a part of the result, if its parent is deleted and its value is not part of the delete set. So basically, let's ask this question essentially. So when does a subtree become part of result. Result is the forest we are looking for. When does it become a part of the result? It's, let's say for lefts, if we have a node like this, let's say we have a node like this. Let me just clarify this a little bit more. So let's say we have a node like this, and we have a left subtree here. So this tree here becomes part of the result if its parent is deleted, if node is deleted. So if we delete this node, then left becomes part of the result, right? So if its parent is deleted and its value of the node here is not part of the delete, because if the node here is part of the delete, then we can't add this to the forest, right? We need to add its children. But if this one is deleted and the node value itself is not part of the delete, then it's part of the forest, right? So this way we can answer our question about when does a subtree become part of the result. It's if its parent is deleted and its value is not part of, its value is not, its root value is not part of the delete set, right? Okay, so this is one of the things we can consider here. Now, the other thing is we know that we should recurse on the left and the right after examining a node because maybe there are more elements to delete there. So that's just when processing a tree, if you want to do something on the entire tree, you definitely need to recurse on the left and the right side, right? So on subtrees, left and right, and remove occurrences of to delete values, right? Okay, now what else can we think about? So when a node is in to delete, so when we find that a node like we did here, it's in the delete set, then we know that potentially its left and right subtrees are part of the result array. Potentially, I mean, because maybe the node is in the delete set, it's the parent node, and at that point we can't add it, but potentially the left and right subtree are part of the forest, but maybe also, like, let's say we have a node like this, right? And then we have this node 1, and we have this node 2, and then we have this left tree and this right subtree. And then maybe here we have another subtree, right? So if this node 2 is the one being deleted, and let's say n1 wasn't part of the delete set, so we'll need to remove this node here. So you can see we have 3 parts that are in the forest. We have this part here, this part here, and this part here, right? And so when processing a node, ideally we would have already done this and would have now to do just these 2, right? But we will need to cut the tie. We need to cut the ties here of this one with the node that was here, right? Okay, so we know this information, so let's see how we can use it. So we know that what we are dealing with here is traversing the tree, right? So whenever you have something like that, you need to think immediately about what are the types of traversals you have on trees and choose one of them, or see which one of them may help you better, right? So the types of traversals on tree we have the following. We have in order traversal, which means basically we do left and then root and then right. And then we have preorder traversal, which we do root first and then we do the subtrees, left and then right. And then we have post order, where we do the root last, where we do left, right, and then root. So thinking about this, which one would help us? So we know that here when we were discussing the problem, there was nothing special about the right side that distinguishes it from the left side. Okay, so that kind of rules out the in-order traversal, because there is no reason to process the right side last and the left side first, right? So we can kind of eliminate this one. And so we have preorder and post-order traversal. So let's try preorder, right, and see if that gives us something. Okay, so preorder traversals means we need to explore the root node first, process it or handle it, and then handle the left and the right subtrees, right? So going like from this remark here, where when does a subtree become part of the result, we said if its parent is deleted and its value is not part of the delete set, then we know to add it to the result set. So how can we provide to a call this information that the parent is deleted? Because checking that the value is not part of the delete set, it's enough to just check, right? And so one thing I'm just going to note down here is that since we get to delete as an array, it's easier to convert it to a delete set so that we can easily check if a value is not part of the delete set. It's not part of the delete array, right? So we can just do delete set first before calling the function. And we could just do that by creating a set out of to delete, right? Okay. Now, we are doing traversals and we know we need to recurse, so let's have a helper function that we recurse on, right? So let's have a helper function, let's call that helper. And we know that we need to pass the node to it. But we said here, if a parent is deleted, we need to know that info if a parent is deleted. And so the node doesn't have access to the parent, but since we are doing recursion from top down, we can pass that information. And so that information would be we can either call it parent is deleted, or we can just say, well, you are potentially the root of a forest, right? So we can just give the method parameter saying you are potentially a root, so saying is root, because parent is deleted means that this node is potentially a root unless it's part of the delete set. And so let's just call it is root potentially, right? So let's call this is root. So now we have the data to do this, right? And so the processing of a node of the root processing in this preorder traversal would be just, since we have this parameter, we can just check if that parameter is true and the node is not part of the delete set, then we can add it to the forest, right? And so the first thing to check before even that is checking if the node is null, because then there is no need to process anything. So if not node, this is just the base case of the recursion, then we can just return node since it's none. Now let's process the preorder step, traversal step, which is processing root, right? So process root first and then we'll process left and right, okay? And so, as we said, we check if its parent is deleted and if the value is not part of the delete set. So we have this root that says the parent is deleted, or this node is potentially a root of a tree in the forest. So if is root and the node value is not part of the root set, so it is not part of the delete set, so not in actually, let's just have a variable that says that. So let's have a variable traversal step. So we can have a variable here called to delete that just says if we should delete this node, and that should just check if the value in the node is in the delete set. Okay, and then here we check if it's potentially a root, its parent was deleted, and it's not part of the and not to delete, then we should add it to the result. So let's just here before calling the recursive function, create a result array. And so we can add the node, right? And so we did the first step of the preorder traversal. Now we need to do the processing for preorder traversal step, and that's processing left and right. And so to do that, well, it's just, we can just recurse, right? So we say node.left equal to the helper function here, the recursive function on node.left. And then we need to pass the second parameter, which says whether this node is potentially a root or not. And so when is a node potentially a root is when its parent is deleted. And we have that information. Basically, we know that the parent is to be deleted if its to delete value is true, right? Because it's in the delete set. So we could just pass that. And we do the same thing for the right side. Now, why am I assigning node.left, assigning the result of the helper function to node.left? Because, well, if we have, let's say, a node like this, right? And let's say n1 here, and then we have n2 here. And we found that we should delete, and maybe we have a subtree here, and we found that we should delete this n2 here because it's in the delete set. Then what that would mean here is that we would have already added n1, right? Because we are processing top to bottom here. So the forest result here would already contain n1 with all the tree content, right? But since we are deleting this, this is no longer part of the n1 tree. And so we need to say n1.left is equal to none, because that would be really removing it. That's what we did here when for the tree 6 here, we don't have 1 attached, we don't have 9 attached to 6 here because we said 6.right equal to none. And this 6.right equal to none is coming from saying node.right is equal to the result. And so the helper function here needs to return none if it's to be deleted. So 9 here, when we deleted it, it should return none to its caller, which is 6, so that 6.right can be equal to none, so that we can end up with a subtree like this one without 6 as its right node. And so that's why here at the last step we should say return none if you are to be deleted. And that info we have in to delete, right? But if you aren't deleted, then you should stay part of the subtree, like the 4 case here. So when we process the left side that has root 4, since 4 is not in the delete set, we should keep 6.left to be equal to the tree starting from 4, right? And so we should return, in the else case, we should return the node itself. And when we process the left side, it will go here again, and if that left side should be part of the forest, it will be added here. And that's pretty much it. We did the preorder traversal steps. Now let's just think about what is the time complexity here, right? So looking at this, we know that we have to explore every node, right? Because we don't know that which value in to delete is which node, right? So we have to explore the entire tree. So that tells us that our time complexity here is O of n. Now, what is our space complexity? So we know that we are using a stack here with the recursive calls, and we know we will do at most the hit of the tree number of them. So we know that at least we have O of h space. But we also have this result array that at most will contain, let's say maybe at most will contain the number of nodes in the tree, right? So at most it would be O of h plus n, but we can definitely come up with a tighter bound because we know that depending on the number of things we will delete, we will get that many forests, right? But those forests will contain the nodes, so let's just keep O of h plus n space. Yeah, so this is the pre-order traversal. But I mentioned here that we can also do the post-order traversal, right? So let's actually first see the implementation. It will be more clear, and then after that we can see the post-order traversal. Okay, so I typed here the function that we just wrote in the overview, the helper function, right? Which was just node is root. We check if there is a node. If there isn't, if it's none, we just return. There is no need to explore further. We have a variable to say if a node is to be deleted or not. And then we check if it is potentially a root and it's to be deleted, we add it to the result. It's possibly a forest. And then so basically this is the pre-order traversal. This is the processing the root node step, and this is processing the left and the right children step. And here we return none to the caller, so that if the node is to be deleted, the parent gets detached from it. Otherwise, we just return the node itself, and here is the initial call that we needed. Now, one more thing we need to do is just call the recursive function so that we can start the recursion here, and we need to pass the root at that point. And then we can return here what should we return? The result, of course. Now, what should be here is this. Maybe it's better to name this, let's say potential root. So should this be true here, or should it be false? It should be true, because potentially maybe even to delete list is empty and we need to add the root, right? Unless it's in the to delete set, right? And that's pretty much it, actually. This is the pre-order traversal. Now, next we'll take a look at the post-order traversal for this. So with the post-order traversal, we actually don't need to pass even this parameter potential root here, because we can just handle so we can just remove this, and instead of doing this here, so post-order traversals means handle the left, then right, and then the node itself. And so we can remove this here, the left side, we can remove the parameter here, and instead what we will be doing here is check, okay, if the parent of these two nodes, the left and the right, is in the delete set, then that means for us is that, so if we delete a parent, then its left and its right side should be part of the forest, right? And we already handled them. So if this left element was to be deleted, was in the delete set, this value here would be none, because we already did the recursive call. And so it's enough to check if it's not none, then that means it should be part of the forest. It's not in the delete set. And so we could just add it right away. And so we add node.left. And a similar argument, or the same argument, is for the right side. So we add it, node.right. Now, if node value is in the delete set, that means for this node, it should be detached from its parent, okay? So that means to detach it from its parent, we just need to return none to its parent. And so for its parent, this node here was either its left or right child, and so this value here would be none. Either this value or this value would be none for the parent, and the parent won't add it to the forest because it was deleted, right? Now, otherwise, if the node itself wasn't part of the delete set, then we should just return the node, right? Okay, so now we did the pre-order traversal processing, except we have one thing that wasn't handled, which is this root node here, because we jump right away into the left and the right side, and then we handle only those. But the root node wasn't handled, and so we need to handle that here. And so if the root value is in the delete set, then we should remove even that root value, right? If it is in the delete set, then we don't need to do anything. But if it's not, then we need to add it to the result because it's part of the forest, right? And we don't need to worry about if a child of the root is in the delete set, we don't need to worry about removing it here, because we will remove it here with this, because we'll change the references using this assignment here, right? and so we don't need to pass this parameter anymore. And here we solve it with post-order traversal. And in terms of time complexity, it's still using the same time as the previous solution, because we are still exploring all the nodes, because maybe the entire set of nodes need to be deleted, because to delete contains all of them. And so we definitely need to look at the entire tree. So time complexity is still O(n). And we still need to have a result array here of all the forests that we get as a result. So it's still at most n, right, for that. And then we still are doing these recursive calls here that are the height of the tree. And so we have O of h here. Yeah, so that's pretty much it for this problem. We solved it with preorder and post-order traversal. There are 2 key points to learn from this one. One is when you have a tree with traversals like this, then always think about which type of the 3 traversals I can use, and of course use recursion for that. And then the second thing you need to think of is, okay, when using recursions, I have 2 tools. I have either the tool of passing parameters inside the function call that I can use, so the parent nodes can pass arguments to the children, and then the children can pass results back to the parent, and the parent can do something with those. And so the parent here just use this info, the return, to know whether it should detach a node from itself or not. And then the arguments that we used in the preorder traversal, where a parent tells its children when it was removed, so that the child knows that, okay, I can just add myself to the forest, right? Yeah, so that's it pretty much for this problem. Thanks for watching, and see you on the next one.